Welcome to the deep dive. Today, well, we're connecting two things you probably wouldn't expect.
Oh, what have we got?
We're taking a fundamental idea from math differentiation, from calculus.
Yep, got it. Rates of change, slopes, all that.
Exactly. And we're connecting it to vacuum-sealed agricultural canned goods. Stuff in your pantry.
Okay, calculus and canned peas. That's different. Sounds a bit like a theoretical exercise.
Right. But that's our mission for this deep dive. We're drawing on some source material actually aimed at college students learning calculus.
Ah, so it's a real application they use for teaching.
Seems so. And we want to unpack how derivatives, that core calculus idea, are actually used to, evaluate pressure changes inside these cans.
Interesting. So figuring out what's happening pressure-wise inside a sealed can using calculus.
Yeah. I mean, most people think calculus is for, plotting curves, maybe physics problems.
There's orbits, motion.
But cans, they just seem solid, static almost. Why bring calculus, which is all about change, into something like a can of beans?
Well, that's the neat part, isn't it? It bridges that gap between abstract math and a really practical engineering issue.
Okay.
Because that vacuum-sealed can, it's not actually static inside. The internal pressure, it can fluctuate.
Fluctuate how?
Based on things like temperature changes, shifts in altitude, if it's being shipped somewhere.
Right. Like flying with a bag of chips.
Sort of. And even, very subtle chemical things happening inside the food over time.
Okay. I think I follow. You sometimes hear about cans bulging if they get too hot, or looking sucked in when it's cold.
Exactly. Those are the visible signs. The pressure inside is changing.
Right.
And here's a key. That change isn't always steady. It might speed up, it might slow down. And understanding the rate of that change is, really important.
The rate is how fast it's changing.
Precisely. It's not just knowing the pressure is some value, say, x psi, at a given moment. It's knowing how fast it's climbing or falling right then.
And the derivative, that gives you the how fast right now number? Is that the idea?
That's exactly it. If you think of pressure as P, and maybe temperature as T, engineers often need to know dP/dt.
The derivative of pressure with respect to temperature.
Yeah. The source material really emphasizes how vital knowing that derivative is. For example, it helps predict if a sudden heat spike in a warehouse might cause the pressure to rise too quickly.
Too quickly. Even if the final pressure isn't necessarily above the can's limit.
Right. The speed of the increase could stress the seal, maybe lead to failure, even if the peak pressure itself, theoretically, should be okay for the material.
Huh. So the speed of change matters just as much as the peak value. That's actually fascinating. Does this math help predict, how long the can's good for under different conditions?
Oh, absolutely. If engineers model how pressure changes over time, let's call it PAT, taking the derivative dP/dt.
Rate of change pressure over time.
Yeah, that lets them analyze not just the pressure at some future point, but the rate it's changing then, and that rate. It influences stuff like seal fatigue, predicting shelf life, especially if you expect temperature cycles during shipping and storage.
So the derivative is kind of the mathematical engine for understanding those dynamic forces inside.
You could say that. It quantifies them. It really pulls calculus down from the abstract and uses it to prevent real problems, spoilage, cans failing.
Wow. Okay. It really shows calculus isn't just for, rocket science.
Not at all. It's the language for describing change. And change is happening everywhere, even inside a humble tin can.
Right. So to wrap it up then, differentiation, that key calculus tool for measuring instantaneous change. It's actually a powerful, maybe even necessary way to understand the pressure dynamics inside something as ordinary as a vacuum-sealed can.
That's the core takeaway, yeah. Abstract math solving very concrete problems.
Okay, so here's something to think about then. If calculus, specifically differentiation, pops up unexpectedly here in canned goods, where else might these seemingly abstract mathematical ideas be, quietly working away in the everyday world around you?
That's a great question. If you start looking for rates of change, for patterns, you might be surprised where the math shows up.